Hello, welcome back to the playlist of lectures on correlation, simple and multiple linear and nonlinear regression models. I am Hemakumar Kasala, and in this fourth lecture in the series, we focus on the topics of polynomial regression and transformations. Study on regression fits is incomplete without understanding the nonlinear regression fits. Polynomial regression and transformations are two main classes within the nonlinear curve regression fits. As part of the polynomial regressions, we understand the quadratic and cubic regression fits, and as part of the transformation-based regressions, we understand how various transformation methods are deployed on the raw data such that a linear regression fit can finally be achieved on the transformed data. Let's get into the lecture. Bivariate relationship can often be nonlinear. A nonlinear curve provides a better fit for such sample observations as the linear least squares line failed to meet the requirements. A nonlinear curve fit is arrived in a similar fashion as the least squares line, wherein the sum of the squares of the vertical distances of the individual observations in the sample to the nonlinear curve is minimized. There are many different nonlinear expressions known that can be deployed depending on the sample observations being handled. Broadly, there are two approaches available. The first one is by choosing a polynomial expression with an appropriate degree k to predict y, as in y hat equals a plus b1 multiplied by x plus b2 multiplied by x square and so on until bk multiplied by x raised to the power k. And the second one is by applying simple transformations to x or y in the equation for the least squares line. For example, as in y hat equals a plus b multiplied by square root of x, where square root of x is the function used to transform x before the least square line is arrived between transformed x and y. Let's understand them in detail. Let's begin with the polynomial expression first. The least squares line equation y hat equals a plus b multiplied by x is a special case of a polynomial equation y hat equals a plus b1 multiplied by x plus b2 multiplied by x square and so on until bk multiplied by x raised to the power k, where k equals 1. Two common forms of polynomial expressions used for the nonlinear fit are y hat equals a plus b1 multiplied by x plus b2 multiplied by x square, which is called as the quadratic regression equation, and y hat equals a plus b1 multiplied by x plus b2 multiplied by x square plus b3 multiplied by x cube, which is called as the cubic regression equation. Let's start with the quadratic regression equation first. Let's understand the quadratic regression fit using an example. Table here provides the sample data from a marathon on average finish time per age group. Representative age is the median age from each age group. The scatter plot of representative age versus average finish time and the least squares line fit for this sample is generated. The scatter plot shows a parabolic shape and the least squares line provides a very poor fit for the observations. R square equals 0.001, which is a very mere 0.1%, and SE equals 56.94, which is a very high value. Residual plot is drawn as well, which confirms a parabolic shape for the deviations, that is residuals, from the least squares line. Considering the parabolic shape in the scatter plot and the residual plot, a quadratic fit, that is quadratic regression curve, is attempted. We arrive at the following quadratic regression equation to predict y value. That is y hat equals 4.62 minus 14.2 multiplied by x plus 0.179 multiplied by x square. There are standard software packages available that calculate the coefficients for quadratic regression expression using the sample data. The scatter plot, that is blue dots, and the quadratic regression curve are plotted. Clearly, a very close fit for the sample data can be visualized. R square is calculated and it equals 0.921, which is 92.1% as against just the mere 0.1% with the least squares line. And SE equals 18.48 as against 56.94 with the least squares line. Residual plot is generated and one can see that there is no visible pattern seen. Let's now move on with an example to understand the cubic regression fit. Let's understand the cubic regression fit via an example. Table here provides the sample data that tabulates the sunshine index versus the cloud cover index. Is there a relationship between these bivariate data? The scatter plot of the sunshine index versus the cloud cover index and the least squares line fit for this sample is generated. The scatter plot shows a double bend curve while the least squares line provides a very poor fit for the observations. Residual plot is drawn as well, which confirms a double bend curve for the deviation, that is residuals from the least squares line. Considering the double bend curve in the scatter plot and the residual plot, a cubic regression curve is attempted. We arrive at the following cubic regression equation to predict y value. Y hat equals 10.9 plus 1.46 multiplied by x minus 7.26 multiplied by x square plus 9.23 multiplied by x cube. The scatter plot, that is the blue dots, and the cubic regression curve are plotted. Clearly, one can see a close fit for the sample data in this case. R square equals 0.62, which is 62%, and SE equals 0.0315, which is quite small compared to the range within the y values. Residual plot is generated and one can see that there is no visible pattern seen. With that, we conclude our discussion on the most commonly deployed polynomial regression curves. We learned that quadratic polynomial regression suits well in cases where the scatter plots or the residual plots as a result of the least squares line fit show a single bend, and the cubic polynomial regression suits where the above plots show double bends. Let's move over to the next class of nonlinear fits, that is transformation based nonlinear fits. Nonlinear curve fit using transformations. Table here provides the sample data that tabulates the velocity of the water in the river versus the distance from the bank. Velocity of the water is the least near the bank due to friction, and it increases towards the middle of the river. The scatter plot of the distance from the bank versus velocity of the water and the least squares line fit for this sample is generated. The scatter plot shows a nonlinear pattern. Increase in y is visibly smaller for larger values of x, and the least squares line does not seem to provide a good fit. Residual plot for the deviations, that is residuals from the least squares line, is drawn, which confirms a nonlinear pattern as well. Let's attempt a transformation on the independent variable distance from the bank, which is x. The transformation by applying a square root function on x and try to fit a least squares line between square root of x and velocity of water y. The scatter plot is drawn between square root of x and velocity of water y, and the least squares line is fitted as shown. The least squares prediction line or the regression line is arrived between y and square root of x, wherein y hat equals 20.1 plus 3.01 multiplied by x prime, where x prime equals square root of x. R square in this case equals 93.8%, indicates a good fit, and SE equals 0.6292 is quite small compared to the overall range of y, that is velocity of the water. Additionally, the residuals plotted against square root of x does not leave any trace of a nonlinear curve pattern anymore. Least squares prediction line arrived after applying a transformation on the independent variable x can be used to predict the velocity of the water y hat for a selected value of the distance from the bank x by first taking the square root of x and substituting the result into the above least squares prediction line. For example, for a selected value of x equals 4, square root of x equals 2, and by substituting the value 2 for x prime in the above regression equation, we arrive at y hat equals 20.1 plus 3.01 multiplied by 2, which equals 26.12. Square root transformation of the independent variable is one among many possible transformations. The list of additional commonly used transformations are listed below. Here are the general tips to choose the appropriate transformation where necessary or applicable. The decisions suggested here are based on the behavior of the observed scatter plots of x and y before the transformation. Square root of x is chosen as the transformation function where the scatter plot shows smaller increase in y for 1 unit change in x at larger values. Log of x is chosen as the transformation function where the scatter plot shows smaller increase in y for 1 unit change in x at larger values. Quite similar to that of the square root of x, the better fit to be chosen based on the statistical results. Reciprocal of x is chosen as the transformation function where the scatter plot shows smaller decrease in y for 1 unit change in x at larger values, and y reaches a limiting value as x continue to increase. Logarithm to the base 10 or the natural logarithm ln of the dependent variable y is chosen as the transformation function where the scatter plot shows an exponential relationship between x and y. A standard transformation table using the power index to choose the transformation in conjunction with the scatter plot shape reference can help choose the appropriate transformation quickly. There are 4 reference shapes for the scatter plots provided. Depending on the shape of the scatter plot that the sample xy data exhibit, one or more among the listed transformations that are appropriate are chosen from the table. For example, if the shape of the scatter plot of the sample xy is similar to 1, then the figure suggests x up and or y up. Look at the blue arrows, which means pick the powers of x and or y which are above in the upward direction with respect to the no transformation entry in the table. Accordingly, the transformation for x and or y is arrived by raising their powers by either 2 or 3. For example, y hat equals 0.01 minus 0.35 multiplied by x prime, where x prime equals x square. If the shape of the scatter plot of the sample xy is similar to 2, then the figure suggests x up and or y down, which means pick the powers of x above the no transformation entry in the table and or powers for y below the no transformation entry in the table. Example, y hat equals 0.01 plus 0.35 multiplied by x prime, where x prime equals x square, or y prime hat equals 0.5 minus 0.73 multiplied by x, where y prime equals cube root of y. If the shape of the scatter plot of the sample xy is similar to 3, then the figure suggests x down and or y down, which means pick the powers for x below the no transformation entry in the table and or powers for y below the no transformation entry. Example, y hat equals 0.01 minus 0.35 multiplied by x prime, where x prime equals square root of x, or y prime hat equals 0.5 minus 0.73 multiplied by x, where y prime equals the natural logarithm ln of y. If the shape of the scatter plot of the sample xy is similar to 4, then the figure suggests x down and or y up, which means pick the powers of x below the no transformation entry in the table and or powers for y above the no transformation entry in the table. Examples are y hat equals 0.6 plus 0.52 multiplied by x prime, where x prime equals inverse of x, or y prime hat equals 3.2 minus 1.53 multiplied by x, where y prime equals y cube. That concludes our discussion on nonlinear curve fits using the transformations table. That brings us to the end of the lecture on polynomial regression and transformations, which is the fourth lecture in the playlist of lectures on correlation, simple and multiple linear and nonlinear regression models. In this lecture, we studied two main classes within nonlinear regressions, namely the polynomial regressions and the transformation-based regressions. As part of the polynomial regressions, we studied the quadratic and cubic regression fits. And as part of the transformation-based regressions, we studied how various transformation methods are deployed on the raw data such that a linear regression fit can finally be achieved on the transformed data set. See you soon back with the next lecture in the series. Bye until then.